In this first episode of our NDT video series, we introduce advanced techniques used to detect surface and subsurface defects in critical components, harsh environments, and high precision inspections. Optical or visual inspection. Optical inspection is one of the most basic and widely used NDT methods. It employs optical instruments such as magnifying lenses, optical microscopes, high magnification digital cameras, and baroscopes to examine a component's surface. The purpose and aim of this method is direct identification of visible defects such as crack, scratch, corrosion, and contaminants. Detecting capability depends on the optical resolution of the system and the lighting condition. The advantage of this method is low cost, fast, and simple to apply, non-contact inspection, and well suited for initial screening and monitoring. But limitations. This method limited to surface and near surface defects and cannot detect deep or hidden flaws. Neutron radiography. In this method, a specimen is irradiated with neutrons and an image is formed based on difference in neutron scattering. Light elements such as hydrogen interact strongly with neutrons. Consequently, materials like water, oil, and many polymers are highly visible within otherwise neutron transparent metals. So, this method effective at revealing non-metallic hull component, moisture, or internal organic material inside metal structures, valuable for detecting leaks, internal moisture distribution, and embedded components. But it requires a special neutron source, expensive and time-consuming, and typically limited to detected research or industrial facilities, and strict radiation protection requires. Laser ultrasonics. Laser ultrasonics generate elastic ultrasonic waves in a specimen by pulse optical excitation and detects returning waves with optical receivers such as interferometer or laser Doppler or LDV. It may be non-destructive or apply with high energy and being destructive. This method is completely non-contact and ideal for hot, moving, or hazardous parts. Non-couplant requires and capable of detecting surface defects and measuring elastic properties, but it requires a high equipment cost and need for precise optical alignments, and also sensitive to reflectivity of the specimen surface, environmental noise, and the system's frequency. TOFD. This method uses diffraction of ultrasonic waves at crack tips. A receiver or positions on opposite side of a weld or test region. Waves diffracted from the crack tips are timed to determine the precise location and depth of the defect. Good reproducibility for large-scale inspections and high accuracy for sizing crack depth and position, but is not a useful method for detecting small and tiny cracks. Therefore, TOFD method is often combined with other, for example, ultrasonic techniques. Acoustic emission monitoring. When a material undergoes crack growth or fatigue, it emits transient elastic waves. AE sensors detect these signals and to analyze can indicate active damage process. It's a good method for monitoring during operation, effective for large structures such as bridges, storage tanks, and boilers. This method is highly sensitive to ambient acoustic noise and requires careful signal discrimination. Crack depth measurement. The objective is quantitative determination of crack depth to evaluate risk and inform repair or replacement decisions. Common approaches include conventional ultrasonic techniques, TOFD and phased array ultrasonic testing, PAUT, eddy current and pulse eddy current, and optical or microscope methods and 3D scanning. Accuracy depends on material properties, geometry, crack orientation, probe frequency, and test steps. Combination multiple techniques, for example, TOFD plus PAUT, often yields the most reliable sizing. Thermography. Consider a wall with a defect such as crack. Heat loss through the area will be higher. Thermography records the surface temperature distribution with infrared cameras. Defects alter heat flow and produce anomalous thermal patterns that can be defects. It's also a non-contact method, also fast and suitable for inspecting large areas and process line monitoring, but its limited sensitivity of depth defecting without advanced processing, and also strong dependency on surface emissivity. Multiple flaw analysis. Multiple flaw analysis deals with measurement and modeling of simultaneous flaw of two or more phases, like liquid, gas, or liquid solid. Techniques include gamma or X-ray densitometry, wire mesh sensors, electrical capacitance, resistance thermography, ultrasonic, time of flight, and high-speed imaging. It's good for predict operational hazards, informs design improvement, and reduce corrosion or failure risks, but requires specialized sensors, complex calibration, and large-scale data analysis. Surface texture and roughness analysis. Surface texture analysis quantifies the microgeometry of surface to access machining quality, microscratches, and wear patterns. Instruments is usually contact profilometers, optical profilometers, optical or SEM microscope, or 3D optical scanners. Thank you so much for your attention. I hope you found this video useful. Comment your questions and subscribe for more tutorial videos. Bye!